Okay, let's see if this is working here. That looks better. Okay, so I've been fiddling around with writing automation in Kerbal Space Program and KOS. And recently there was an announcement that somebody has written a similar program called Control System 2 for Kerbal Space Program 2. And I thought I'd give it a try. Been puttering away with it. It has much more of a feel of a modern language like Rust, whereas KOS tried to stretch for a retro feel with, kind of ancient Fortran, I think was the original idea of making it look like code that we would have used back in the 60s in the Apollo program. So, big difference in the feel of the code. As a result, I make all sorts of errors when I write it because I'm going back and forth. I'll do things like I'll go to Kerbal System and I'll type in some stuff and I will end my statements with a period, which is what you do in KOS, but not in Control System 2. KS2 provides, well, the flavor is you do more functional programming and you put more as a goal, you will keep things immutable, and it kind of encourages some better practices, like you would expect out of modern programming language. It has a package manager built in, for example, so no more faffing about wondering whether I should use this manager or that manager or whatever. Anyway, so we have a console here. Control System 2 is centered around the idea that you are automating something that's happening here at ground control. And as the ground system engineer, you will pick one of the entry points and trigger it, and it will manipulate the rocket you're looking at. So there's no state kept on the rocket. In fact, there's no global state I could find at all. You just trigger things, and you can do things like if there's parameters to the entry point, you can click on this and you say, well, I can tune these things. And in fact, my Tinker script that I'm using, I have the ability to specify a target altitude and a initial heading, which is kind of your launch azimuth. These up here, these are all stock. They come with the app. So for instance, Launch Rocket showed me how to do that. Anyway, I'm going to stick with the default right now. What we're launching, this script actually works with the stock Kerbal K1 and K2 rockets, but I thought you might like to see something a little interesting. So this is a asparagus configuration where I've got a center core and I've got 3 pairs of outside cores that are going to drop away. So the first core pair will drop away when it's empty, and it will have been trying to feed the rest, and so on. And the second core when it's empty. Fuel ducting doesn't work quite right yet under KSP-2. It does work somewhat, which means we get some fuel sent from the first pair to the second, and from the second to the third, and the third back to the middle. But we don't keep them full. And I've actually done videos on that before. It's still there. They're working on that for patch 2, I believe, which I'm looking forward to. They fixed a whole lot of things. KS2 has fixed a number of things that have allowed me to get this far, so I figured I would show off what we've got. This is all, this is actually 0.2. This is the latest version. It still has a slightly older version that shows up here. The only difference between 0202 and what I'm actually running that's the latest is, for instance, apoapsis. It recognizes that there are hyperbolic orbits. Some trivial under the hood things. But what I'm doing here really is possible under 0202. I am sure that at some point the version number on the display panel will be updated. Anyway, so let's launch this sucker and watch it as it attains an orbit. It will be doing a gravity turn and then coasting to orbit and then circularizing. Real simple. And let's watch it do that. I have set up the script so that instead of automatically launching, it's going to wait for me to hit the button. Now, the script has complete control over the throttle. Because of the way things work, I needed to get control and set up the managers as part of my initialization, and my actual code that's running just keeps control over it and just maneuvers it around as it wishes. But that means that I can't really adjust this by hand, or it's going to snap back to what my script wants. But I did leave it up to the engineer to hit the go button, so we'll hit go and launch, and it's probably going to be pretty loud. Let me back way off here. That's not too bad. I love the new sound. A little crackle from the engines. I could probably make that even a little louder. I turned it way down because I was worried about it. Yeah, that's fine. So you'll notice that during the gravity turn, we're not pinning exactly onto prograde. Now, if we did a perfect gravity turn, we'd be burning exactly prograde and we'd have no cosine losses at all, and it'd just be beautiful. But this particular vessel has too much thrust to do that. So instead, we have a gravity turn that we try to impose, and because we have too much thrust, our actual trajectory will be somewhat higher than what we steer. Fortunately, when we get up to this point, let's set this to sea level and go to orbit here. We get to this point, we're done burning because our apoapsis is up around the 80 kilometer mark, which is where we want. And my scripts currently just burn full throttle until your altitude is high enough, and then they cut it to 0. That's because my first orbit, I'm not doing a precision orbit, I'm just getting there. And burning full until you're high enough and then chopping the throttle gets us there, and it took very little work. So the coding was easy on this. That was what I was looking for. This is a Tinker script. You can see the name is Tinker. So the second thing is circularization. I have messed around with maneuver nodes, and there was a couple of problems. If I programmatically create a maneuver node, I can see it, I can look at it, I can ask the maneuver node to please tell me what the burn duration is, and so on. But as I do the burn, it doesn't update the burn vector and the duration. So you can't do the KSP-1 trick where you keep looking at the maneuver node burn vector, and it gets shorter and shorter and shorter until it's done, and it swirls around. So instead, what you have to do is look at the burn vector initially, figure out what your final velocity needs to be, and then write an error controller to make your velocity equal to it. I thought, well, let's go back to my original circularization where it's just an error controller, where I say, starting at a certain time, I'm going to burn. And what I'm going to do is I'm going to say, if I were in a circular orbit, what would my velocity be? And then look at my current velocity and say, well, I've got an error here, so I'm going to burn to correct that error. And that turns out to work very well. So I am not circularizing at a specific altitude. I am not saying circularize exactly at the apoapsis. What I am saying is circularize at a specific time. And Circ AP says that time where we start circularization is the apoapsis. So we're going to end up with a circular orbit at some altitude slightly less than our initial apoapsis, which is okay because our launch to altitude is not a precision launch. Maybe someday we'll do a precision launch to altitude and a precision circularization. We'll probably do it by launching higher and then doing the circularization as we cross the radius. But that's for future work. Again, because I've broken this up into pick the time to do the burn and then do the burn at the time, circularize at AP, circularize at PE, circularize at a random radius, those all use the same bit of logic, which we just saw run. And that fast, you notice we're done here. We're at 77.7 kilometers. And that error is on the order of 100 to 200 meters. And we're done that fast. So let's take a look at some of the code that's involved in doing that. And those of you who don't look at code, you can feel free to drop off. I will put a link to the repository. I've got my TO2 local directory in Git, and I've actually pushed it out to GitHub So you should be able to grab these scripts and use them if you want to under Control System 2. So I'm going to revert to launch, and I'm going to bring up the code. I think I'm going to turn off the webcam because I'm taking up too much space on the screen. Okay, so TO2 local inside the mod area. You go dive down deep into the mod area, and you eventually come to a directory which has a thing called TO2 and a thing called TO2 local. TO2 are all the stock scripts and libraries, and he has stuff in there to do all sorts of neat things, execute maneuver nodes and orbit and all the things I wanted to do. But I like working at the low level. I wanted to stretch my wings and actually write autopilot code to achieve the launch, achieve the gravity turn, and achieve the orbit. So all of my code here is kind of self-contained. I, of course, use the mod like crazy, but I'm not dipping into the standard library to say, oh, just do me a grav turn. I wanted to work that out myself. So my main executive, trying to make it so that eventually we can just have an array that says, here are the steps to go through for my mission. Here's my mission plan. In this case, my mission plan is a manual launch followed by lifting off. So we do a little bit of logic right as we lift off to get clear of the gantry. We do not want to slam ourselves in the gantry, so we need to lift off upward. We slip into a gravity turn, and that will control us all the way up until we are done with the turn. We want to coast into space. We don't want to start planning our circularization really until after we've got it into space. So we space coast, which keeps us pointed aerodynamically and gets us up into space. And then circap will say, we are going to circularize when we get to apoapsis. And then we drop into this last one, which says, just do nothing forever. These are all functions that will return a Boolean. True says, call me again in a moment, and false says, I'm done. Very, very simple. There is a background task that runs as part of this. So you notice we have this synchronous phase loop. Sync phase loop says, this is a synchronous function. This is an important concept in 1202, is that these lambdas, these closures, are marked as synchronous. So inside Unity, they run synchronously. They're not async. Most everything in KS2 is going to be asynchronous, so they can coexist happily with Unity, but stuff that's synchronous can't. So all of these synchronous functions, they have to run very quickly and do their job and get out of the way. Now, they are compiled down, so we can do some pretty significant things before we impact, but I've had cases where my code got too complex, and if you hold off the main loop of Unity for too long, it will crash on you. So there is some risk in that I'm running all of these mission phases as synchronous tasks within Unity. Oops. I'm hoping to get away from that, but I will need a way to be able to pass around a reference to an asynchronous function. I'm sure there's a way of doing that. If there isn't, I can talk to the mod author and maybe we can work out something. So inside the synchronous phase loop here, so this is all embedded in the mission. Basically what we do is we say, while phase, self.tick. And self.tick is this tick function which runs at the end. Basically my mission's execution is we run a step of a phase. So a phase is like a gravity turn. So I run some quick computations for gravity turn. And that's an iteration of my main loop. And then at the end of each main loop, I run background tasks. Currently, because background tasks need to be asynchronous, I can't have a table of them. I can't use lambdas. I have to actually hardwire them in. So Tick knows about this automatic stager. So our components of our mission are the mission steps here and the background tasks that we actually have to hard code into Tick right now. So stager, let's take a look at stager. It's the first thing to do any significant work. Stager says, if staging is needed, then do the staging. And this call right here, staging.next, this is an asynchronous call into the KS2 libraries. So because this is asynchronous, its caller is asynchronous. I cannot do a synchronous function calling an asynchronous function. Again, maybe we can work out how to do that. Maybe there's a way of doing that I don't know yet. But right now, if I call an asynchronous function, I have to be asynchronous. So I say, if staging is needed, then stage. Well, when is staging needed? Here's the function. If my current stage is stage 0 or 1, now there's two ways of numbering stages in KSP-2. What it's showing here on the UI off on the right is a stage number that's presented to the user, and it's 1, 2, 3 from the bottom of the rocket. But the actual stage numbers start out with 0 at the top of the rocket, and they increase. So internally, it's the same stage numbers as in Kerbal Space Program 1. So it goes 0 at the top through n, and as you stage, n gets smaller. So you're on stage 8, and you stage, and you're stage 7. From the user side in KSP2, you're on stage 1, you stage, and now you're on stage 2, and you stage, and now you're on stage 3. So the user interface and the numbers inside are not the same. They go opposite directions. So this 2 greater than staging.current says that if we are already on stage 0 or 1, then we don't do any more automatic staging. And my intention here is I normally put parachutes on stage 0 and on the top stage, and I do not want to activate the parachutes with the auto stager. Now, this could be off by 1, but what I do want to do is I want to, if I've got the parachutes on the top stage, and the next staging down is a stack separator, I want to fire the stack separator. So I think this may or may not, I'm not sure whether this will fire the stack separator or not. We'll have to experiment. I haven't run any missions all the way to completion yet, so this 2 may become a 1. It needs debugging. Anyway, so basically this says, if we're out of stages, return false. And staging needed, returning false says don't stage. Then we check mission elapsed time. And that comes from my common area. I have a common structure that carries state of the mission, which is common to all of my modules. And it's got a method called MET, which will calculate the mission elapsed time. And that will be negative before I launch. And the moment I launch, it will start at 0 and go upwards. Now, in the case where we have a planned launch, MET will be like -10, -9, -8, and so on. If you're just going to launch based on keyboard input like we did here, it's stuck at negative something, and it'll just stay constant until I hit the space bar, and it'll jump to 0 and go. The effect there is that if MET is negative, we haven't launched yet. If we haven't launched yet, then for God's sake, don't stage, because if we stage and we haven't launched yet, that means we're going to force a launch, and I'm trying not to have the stager force a launch. Next thing we say is, do we have any available thrust? Well, if we're not on the last stage and we're launched and we don't have any thrust, it means that we probably have staged into a stage that has no engines. So it might have a stage that activates an engine, and the next stage is a separator, and the next stage is an engine. So if we've got 0 available thrust, we want to stage again in an attempt to ignite the next engine. And we may stage several times depending on what the separators are. So if we do have thrust, now we go out and now we do the expensive thing. We go count the number of engines that are flamed out. And actually, I don't need to count them. For my logic here, I could just stop when I find the first one. If anybody is flamed out, then we do want to stage. So is 0 not equal to flame out count, then return true. And if nobody's flamed out, we drop through the bottom. There may be other times we would want to stage. but we're returning false. So some missions may want to say, "Oh, I'm about to enter the atmosphere, and I've got a big old honking engine attached to me that isn't really good for atmosphere, and it's got fuel, so it's not going to stage normally. Let's get rid of it." That's something in KSP-1 I called the lighten phase. It wasn't done automatically, but that sort of thing could go in there. So counting flame out. How do you count the flamed out engines? KSP-2 doesn't provide me as much information as KSP-1 did. I can't say count the engines that will, what I'd like to do is say, show me all the engines that would be discarded if I staged, and then see if any of those are ignited and not flamed out. So if an engine is running, I don't want to discard it, right? Can't do that. KSP-2, I can see if an engine is ignited or not. I can see if it's flamed out or not, but I can't see whether it will be discarded on the current stage. I can see which engines are currently active, but in a asparagus configuration like this, an engine will be active for several stages. Oops. Okay, so the best we can do is run through here and say, take a look at common vessel staging, parts in stage. So this will get us all of the parts in the current stage. And that includes all active engines, even ones that are not going to be discarded. So we've got all that. These are lists, and lists have a dot filter. So I can take one array and you dot filter with this condition, and this will produce a new array that only has the parts that are engines. And then we filter again. And now we get only the parts that are engines and has an engine module defined. Now, these two should be the same, but I wanted to make sure both conditions were true. And then we go through and we do a map, which says take all the parts and convert each part into part.engineModule.value, which gets me back an engine module. It's a different data type. And inside the engine module, we now want to filter and we say, just keep the engines that are flamed out. This will give us a list of engines that have actually flamed out, engines that have no fuel. We're going to take the length of that array and return it. So this will give us the number of engines that have flamed out. Now, in theory, I could simply iterate through this common.vessel.staging.parts in stage, whatever. So this first two lines, I could take that array and just iterate through it, and then go through and look at each thing and say, if the part's an engine and it has a module defined, we'd say if this and this, do this, if this, return true. So we could stop when we find the first flamed out engine for what we're doing here. But I wanted to keep account of them. The idea I had in my head was, it could be we're in stage 5 and we've got two different engines that are going to flame out in stage 5, but one's going to flame out before the other. So I was going to wait, I see one flamed out, I was going to wait a moment and see if the other flamed out so that we get both of them flamed out. Then I realized if there's a long delay, now I've got a long delay anytime I see a flame out to see if anybody else flames out. That's no good. So we can't handle two engines flaming out in the same stage that are going to be discarded by the same staging event that happen at different times. So design rule, if I've got one engine that flames out before a certain stage event, all the engines that are going to be discarded by that event have to flame out at the same time. Otherwise, we're going to discard both of the engines that are in that stage. One of them's flamed out, one hasn't. The one that hasn't is going to be firing, and it's probably going to, run into us. If we build a rocket that violates that design rule, that means that here, where I do this staging next thing, what I need to do is first cut the throttle to 0. Second, do the staging, and third, bring the throttle back up, which means I would need to be able to generically be able to say, please suppress the throttle independent of what anybody else in my code is doing. Now, some of my code is setting the throttle to a given value, which is easy enough, but some of it is using a function to compute a throttle value, which means I would have to have a front end somewhere that said, oh, and if the stager needs to suppress the engines, we'll suppress it here, which would mean basically perturbing every one of these throttle computation functions, or having every one of those throttle computation functions wrapped in a caller, which still has to call them, but then has to quash the output, which means that We still have to call it because I sometimes do things in there other than compute the value. But that would also mean that, if we've got one of these things that computes a delta V vector, sets the steering, and then does a bunch more computation to come up with the throttle, it means that we have to do the first part. And since we're not putting anything in the middle, it means we're forced to do the second part, even we're going to throw away the result. So I am hoping I can get away with not quenching the throttle here. The other thing I could do potentially is release the throttle, tell the manager to do a throttle release, do the next, and then do a resume. So release and resume. I don't know, can you query to see if it's released? What if we release the throttle in the main line? We would release it again, we would stage, and then we would resume it when the main line doesn't think it's resumed. So we have to think about how we're going to handle quenching the throttle or releasing and resuming it. All these are problems that I'll have to think about, but what I wanted to do with Tinker is just get this to work. So for now, we leave the engines going and we stage. We just say, if I'm going to discard 2 engines, then they have to flame out at the same time. Fine. So that's Stager. Stager works. I have tested this out on K1 and K2. I've tested out on the asparagus stuff. I tested out on a couple other fairly strange configurations. Like I said, the weirdest is if you have 2 engines that flame out in the same stage but not at the same time. And what I found out was that pretty much it's very hard to construct a sequence like that where you maintain symmetric thrust. It's almost a onion configuration where the outside ones flame out and then the middle one flames out, but you're not discarding the outside ones. The outside ones flame out and you can't jettison them, but you're still burning the one in the middle. And that is a bad design. So I think we can say any rocket that is stable and has some engines flaming out and not others is a bad design, and we can fix it. So I believe the Stager is going to work. But I've done this before. I posted a Stager to Reddit and immediately got a whole bunch of feedback, including some really good efficiency changes for KSP-1. Speaking of, the hack for KSP-1 is you watch your available thrust. And when available thrust goes down, that's because some engine has burned out. Okay? Which means that instead of iterating through the engines every time, I can just watch available thrust. Well, in KSP-2, available thrust does not go down when an engine flames out. It stays where it was. So I can't just say if available thrust less than previous available thrust, then we must have had a burnout. So anyway, so this is as small as I've been able to make it for KSP-2. I can make the code more compact by taking a lot of these braces around one line, removing the braces and moving the line up and so on, and making it smaller and all that. But I prefer to keep my code readable when I can. So now let's take a look at the launch sequence in order. Let's start with the launch methods. Let's see. Can I fold the code real quick? Okay, K0, control K, control 0. Okay, so here is, I put my phases in groups. So for instance, the launch file has 4 phase functions. So we can call launch time, which will select a time to launch. We can call countdown, which does a countdown and then terminates the countdown at the moment of launch. And then liftoff does the actual liftoff. It gets you above the launch gantry, just barely above it. It's very short, but it assures that you have full throttle until you're that high. And manual is added later, which is why it's at the bottom. And manual waits for the engineer to hit the go button and then goes, and dives into the next step. Let's take a look at these. I'm going to do them in the order I wrote them. We're not using launch time currently in the Tinker because we want to do it manually. But for automatic, what we do is we set this common.t0 to the desired launched instant. So common.t0 is going to be t0 for the mission. And if it's in the future, we haven't launched yet. And all these guys are going to return false to say that we're done with that phase. They're going to return true to say, call me again in a moment. So that's launch time, real trivial. Open for expansion. If we start building missions that want to launch to a given orbital plane, then launch time can look in common to find the constraints, and it can find a launch time that meets the constraints. That also works if we're trying to meet a launch window for a interplanetary transfer. We may want to sit on the ground for 3 weeks and then finally launch when we've got a good transfer. Although I think that for my purposes, what I want to do for the interplanetary is get myself in a high orbit around Kerbin and then basically stall in the high orbit until it's ready to leave my interplanetary. I think that's actually more my style than waiting on the ground. Countdown. We enter countdown at some time, who knows when we enter. We're going to be calling this repeatedly if we haven't launched yet. So we called launch time and it's set up at T0. And we get into countdown. We say, well, we want to start a countdown. First time we get in here, this is a model you'll see a lot, where inside the launch structure, I have a mode number. Probably mode is a bad name, but I couldn't think of a better name. You say if it's not 1 yet, then set it to 1, meaning this is the first time we call into countdown. So 1 means we're doing countdowns. And if it's not 1 yet, it's our first call. So we say it's 1, and I'm going to store what time we started the countdown stuff. This turns out to be useful for debugging. Currently, nobody's using it, but I'm going to keep them because having it there means I can turn things on in debugging. I can set things up and print some things in debugging. I don't have to go back and rewire all of it. So set mode to 1, set UT to 1, and print something. This guy really doesn't do anything else. But what it does do, it doesn't do anything else in the first call. And every call after that we say, find out how long it's going to be until our T0. Then we figure a countdown number, which is going to go 4, 3, 2, 1. And that's the ceiling. So when we go down to 3.6, it's still going to be 4. And when we go down to 3.0, it's going to be 3. If we go down to 2.999, it's going to be 3. So the moment we change, this countdown changes, we want to print it. So we store it here. We store the countdown number we have most recently printed. So we take this guy, this is an integer, and if it changes, we're going to store it. And if it's in the range of 0 to 10 inclusive, then we're going to print it. So we're not going to print T minus 15 or T minus 12. We're not going to print T minus minus 5, but we'll print T minus 10 through T minus 0. Actually, we don't print T minus 0. And then down at the bottom, we have a condition. Remember, the condition true says countdown is done. So countdown is done when DT is greater than 0. Well, when countdown returns true, it says call me again. So return false when it's done. So if DT is greater than 0, if we're not at T0 yet, call me again. So we'll keep getting called until basically current time catches up with T0. Next thing is liftoff. Liftoff says we grab some state. So again, we have this self thing that is state for all the launch things. So any phases within launch can communicate state to each other through this structure. And it has a reference to the common structure that it can use to communicate with phases in other files. So common contains a reference to the vessel. This is how you get to your vessel. You don't have a global variable that you reference that says the vessel. It's a vessel, and it's passed to your code when you start. Your main entry point gets handed a vessel, and it's expected to hand it to everybody else. So I tucked vessel inside common and hand common to everybody. Common has a whole bunch of other stuff in it. So mode's not equal to 2, then this is our first time calling liftoff. Okay, so first time we call it, I need to know when it ends. We are going to be moving upwards for a certain altitude. So there's a launch height. we want to retain control until we are above that height from where we started. So when first time we come through, we sample our current altitude, so we know where we're starting. And then we say, well, if we're starting at, you say, over here, we look at this and we says, oh, it's 123 meters above sea level. Is that showing? That's not showing. Okay, so we're sitting on the launch pad here, and we're at 123 meters above sea level. So that's fine. We'll sample 123 here, and we'll add in the launch height. Launch height is how tall the gantry is. I measured this by basically launching a vessel that moved slowly and then watching very carefully to see when the engine bells cleared the launch gantry. And then I wired that down inside launch height. And that was 36 meters, but I'm leaving it here because that's an estimate. And I may get a better estimate, or there may be a way of querying. It could very well be that different launch pads have gantries of different heights. It could be the launch pad gantry will change size based on the vessel. I don't know. But there it is. I can tune it by editing the code. The mission itself can reach in and change the launch height. Always does so before we do this. So the first time through, we're going to calculate our altitude plus launch height. So this is the altitude we need to be at for everything to be done. So it's the first time through. We stash off T0. So the first time through liftoff, we're going to call that T0. Whatever else we've done, that's T0, even if it's not what we planned. I'm going to force the throttle to full, so we always start off full throttle coming off the launch pad. Enable the autopilot and turn on stability assist mode. So the SAS is in stability assist. It's just trying to minimize our angular rates. So if we start to turn, it will try to lock us in place. Even if it isn't returning us to upwards, it's at least stopping us from tumbling, which is what we want. We don't want to be doing all sorts of weird things coming off the launch pad. And I'm going to print something pretty consistently with all of these phases. I'm going to do a print line saying which phase step is beginning to run. So we'll get a little bit of output over here. You saw that when we did the launch. So this all happens only the first time we call liftoff. After that, we just run through and we say, well, we are done when the vessel, if the vessel altitude is less than the liftoff done, call me again. So as long as we are not yet high enough, we stay in liftoff. And once we get high enough, we're done. We got a chatty kitty over there. The next thing is the manual launch, which got added later, when I realized that I really did want to just have control from the keyboard. I didn't want to be just, you start the Tinker script going and it launches. I wanted to be able to start the Tinker script going and have the go come up later. We have a kitten that wants to be held. Hold on a second. Okay, this is Lucy. She's my co-pilot. She helps me code. So she points out where things have bugs. And she gets between me and my microphone. She gets between me and my keyboard. Gets between me and my dinner. Gets between me and everything. She doesn't always want to be held for very long, but if you don't grab her when she's meowing, she will meow. Yeah, she's twitchy. Okay, camera off again. Ba-da-boop. Bink. Okay. So, where was I? Manual launches. So this got mode 3, even though, so the mode numbers aren't really in any particular order. It's just, the order that I put them in. So these would be an enumeration. I should have just set it up as an enumeration. I don't know whether it's in the language yet. Who knows? Anyway, so mode 3 is we're doing a manual. So first time we come through, we want to store some things for mode 3. And wow, what is that? We've got some computations we're going to do. I'll go into that in a second. But the other thing we want to do is when we enter mode 3, we want to set the throttle to 1. Now, by default, when the script boots, we've got our throttle set to 0. But we're exercising explicit control over the throttle. So, yeah, when we're locking the throttle at 0, if the user tries to change the throttle, it doesn't change. Now, it'll change right now because no script is running. But if I start the Tinker script going, waiting for launch, notice if I snap the throttle down, it snaps back up. Oh, there's a sunset. Cool. Okay, so we set the throttle so that when the engineer hits the go button, we start launching. If we don't do that, then the engineer hits the go button, the launch clamps will let us go, and the ship will fall until we finally get the throttle up. And there may be a delay. I'm not sure how often manual is going to get called. Our main loop is not running timed. It basically is just calling it back to back to back to back. And it's got a sleep in the middle there. I mean, I do a delay. Let's take a look at it. How much of a delay am I putting in tick? I'm not guaranteeing anything. Oh, I do a sleep 0. So I'm sleeping for the minimum amount of time, but that means that Unity is going to go off and do other things, and we'll come back when we come back. And that might be in 1/100th of a second, or it might be in 1/4 of a second. Who knows? Anyway, so we get the throttle set up and print awaiting launch. And now our termination condition, which is what all this math is for, I want to come out of manual when my available thrust exceeds launch thrust. So when I have enough thrust to leave the launch pad, that's the instant when I want to say, we're go. I'm admitting the possibility that we may have to stage several times. The user may have to, you stage once and it activates some boosters which aren't quite enough to get you off the launch pad. You stage again and it activates more boosters which aren't quite enough to get you off the launch pad. Then you do a final staging and you finally get all your engines going, and now you've got enough thrust to get off the launch pad. We call that T0. At that point, manual is done. So if the available thrust is less than or equal to this launch thrust threshold, we keep calling. Now, what is the launch thrust threshold? Well, it is the amount of thrust necessary to cause us to accelerate upwards. So that's the gravitational parameter of the body times the mass of the vessel divided by twice the radius of the body. So mu over r squared is the gravitational constant of 9.81 meters per second. So mu comes from the gravitational parameter of the body. 9.81 is correct for Kerbin, but I'm going to use mu and R2. So mu from there, R0, this is the radius, and I'm going to go ahead and use the correct radius for the vessel. So that's body radius plus the vessel above sea level. Now, vessel above sea level is only going to be a very trivial correction to the body radius. I mean, who cares about it, right? But put that in anyway, just to be correct. R squared, vessel mass, so thrust is mu times m over r squared. Now, I tried to do all this as one expression, and I had a heck of a time. I kept getting 10 to the 14th. Anyway, so I decided to just, wrap it all up in the individuals. Part of it was I broke it out like this, and I started printing things to make sure it was sane. And when I broke it out and started printing it, it started working. So I removed the print statements, and I'm just saying, don't touch it. It works. Waiting launch, and there we have the launch. That gets us launched. I have made a change. Next is the ascent. Similarly, ascent is a collection of steps. Ascent handles the gravity turn and space coast. So not a whole lot to it. We have some state. We again keep our mode, and we keep the time that we entered the mode. I'm doing mission elapsed time. This is how I originally started, and it wasn't until I started doing the launch stuff that I realized MET was not a good thing to store for launch stuff. The other thing that Ascent needs to know for the gravity turn is, as I'm doing a gravity turn, there's a minimum and a maximum altitude. The minimum altitude, we're going to be pointed as high as we can, and at the maximum altitude, we're going to be pointed level. So we're going to configure those here, and we're going to tune them on our first call. We'll see how that works. So, get into gravity turn. We do need the vessel in the orbit. We pick up our desired apoapsis, which is the launch altitude. So the goal of the gravity turn is to push our apoapsis to or above the launch altitude. And great precision is not required. And then we have the observed value. And this is our first termination clause. So if we currently have an apoapsis that is above the launch altitude, then we're done. So we print gravity turn complete. We kill the throttle, and we tell the SAS to keep us prograde, and we're all done. So there's our termination. We check that first in. We may be terminated on the first call, depending on when this happens. I'm still thinking in terms of KSP-1, where I could reboot the system in the middle of a gravity turn, for example. I don't know if that applies here. So if we're not done, then we say, well, okay, is this our first call? First call, we store stuff, and then we configure the minimum and maximum altitude. Well, we are going to say, start with our maximum pitch upwards at the current altitude. So instead of, if I set this to 0 and we're at a higher altitude, that would immediately snap us to a different pitch. I don't like snapping us. So we're going to start out with, at our current altitude, we're going to have our tallest pitch. And the maximum altitude is going to be the depth of the atmosphere of the body we're around. And just in case we're launching from MUN or MINMUS, we're going to say, well, if atmosphere depth is 0, we're going to say that the gravity turn is going to take place between current altitude and current altitude plus a kilometer. So we're going to give us 1 kilometer to snap ourselves over to horizontal. That means that we're going to give a kilometer worth of clearance to obstacles on MUN and MINMUS. I'm thinking the kilometer might not be enough. So when we start launching from MUN or MINMUS into MUN and MINMUS orbit, I will change the gravity turn radius here to make it more appropriate for the particular body that we're orbiting. First time into gravity turn, well, normally we start when we've been going straight up and we've just gotten beyond the launch gantry. So we assure that the throttle is set to full, and we assure that the autopilot is set to autopilot. So the SAS in autopilot mode, so that we can give it a direction, a target orientation. That's good. We do this only the first time. We only have to manipulate the autopilot the first time. After that, every time we get called, we have to do the same thing, which is work out what fraction of the atmosphere we have gone up through. I'm going to pull that down temporarily. This is the vessel altitude minus the minimum altitude. So I can start at 0 and go upwards, unless, of course, we manage to end up at an altitude lower than our starting altitude, in which case we're not going to space today, but anyway. So our altitude above where we started divided by the maximum altitude above where we started. Okay? So that goes from 0 to 1. And it might be less than 0 if we lost altitude, or it might be greater than 0 if our current altitude is above altmax. And that probably will happen on MUN. We may end up exceeding our kilometer. There. Control Z that so that it's no longer modified. So 0 to 1, maybe beyond 0, maybe beyond 1. We clip that to be strictly in the range of 0 to 1. I'm going to take the square root of it, because what we're going to do is use that as a fraction to run from 90 degrees down to 0. And if we do it linearly, you end up with too shallow of a gravity turn. And by using square root, that bellies it up a bit. So we end up with firing upwards a little more. Is that right? I have forgotten what it is, but basically as you go from linear to square root or 0.4 or 0.6 as the exponent, it changes the curvature of your gravity turn. And square root was better than linear and good enough. And there's probably exponents that are even better. I think Cheers Kevin worked out that for what he was looking at, 0.4 was best. But I think that if you are trying to optimize that exponent, it's going to be different for each craft. And square root seems to be good for everybody. Not perfect, but good. I think at KSP-1 I give up maybe 100 or 200 delta V from the optimum. So square root runs from 0 to 1. Pit frac will run from 1 to 0, so it'll start out at 1 and it'll go towards 0. So pitch now goes from 90 down to 0, and we are assuming that we're starting at 90 degrees. If we wanted this to be able to pick up anywhere, well, really because of the square root that's in here, we would need to actually store the alt-min anyway. So we can start off with 90. In normal circumstances, we will be starting the gravity turn from pointing straight up. So all we've done is we started straight up and we had SAS mode in please keep us stable. So we should be, within a fraction of a degree of pointing straight up. Close enough anyway. So there it is. We have a launch azimuth. And then we say, okay, so we want to have our vessel on a heading. So normally launch azimuth of 90 is east. So we want to head east with that pitch up from the horizon. So 90 is the directly up and 0 is the horizon, and no roll. So this direction would actually be the correct direction that gives us a wings level flying in the azimuth direction and the appropriate pitch. However, target orientation doesn't take a direction, it takes a vector. So using vessel.autopilot.target organization will take the current pointing of the craft and will rotate us as simply as possible to put our forward vector in that direction, even if we're not rolled. So we are not actually controlling the roll. So in effect, what we're doing here is we're going to head up and we're going to kind of lee over onto our right-hand side, and our nose is going to point in the right way, but our head is going to be pointed, sideways or down or up or midway in between or wherever. So it's kind of random. In practice, it seems to be stable. I've noted KSP-1, if you tried to do orientation using just vectors, sometimes you get into uncontrolled rolls. That hasn't happened to me yet. So this will continue. So true at the bottom. It always says if we go through this logic, we always want to be called again. So every time through, we're going to do all this computation to work out the new pitch, the new direction, and reload the autopilot. Until finally, at some point, our actual apoapsis exceeds the target, and that'll return false. The next step is the space coast, really super simple. Again, if we're not in 4, we go to phase 4. One of the reasons I do this is so that we're no longer in 3. So if we went back to phase 3, it would start over again. We're never going back to phase 3. So get into space coast, it says we are coasting, so we want to shut the throttle off. We want to turn the spacecraft in prograde. This probably should be surface prograde. I keep thinking about that. I never managed to change it and print something. This is going to coast up, keep our nose pointed prograde. When are we done? Well, we're done when the vessel altitude is above the atmosphere. So if the vessel altitude is less than or equal to the atmosphere depth, call us again. Atmospheric depth is vessel main body atmosphere depth, and the altitude is vessel altitude sea level. So that's how we park ourselves in the space coast until we get to altitude. And once we're done with that, we head on into the orbital code. So this is the circularization code. I knew when I started this video it was going to last a while because circularization is it's the interesting bit. So, circuit AP doesn't say circularize at the correct altitude that we currently have our apoapsis at. It says when we get to our apoapsis, initiate a maneuver that will correct our orbit to be circular. And there's a difference there. I fiddled around with maneuver nodes. I wasn't able to make a good maneuver node follower because the node itself doesn't track what the remaining delta V is. You have to do that yourself, so you're already building an error controller that says burn to reduce this the error in my velocity. So it was just easier to write the error controller for burn until we are in a circular orbit. So Circ AP says, I think I have lines in here I don't need. I do need orbit. Okay. It says, put us in mode 2. So mode 1 is going to be the actual worker B that does the work. And we're skipping down to 2. So mode 2 is planning out a apoapsis circularization. So first time through, if we're not in 1 or 2, then we go to mode 2, print something out, and we say burn universal time. So we set our starting burn time to this value here. So we say, hey, orbit, when is the next time after 30 seconds? So at least 30 seconds from now, when after that do we get to apoapsis? And this has a weakness I just realized in that if we do this on a launch and we don't get to here until 10 seconds before apoapsis, so we've got to do here, if periapsis, if we would get to periapsis before apoapsis, then do it now. So normally, I'm going to leave the logic the way it is because this is working, but normally it says, starting 30 seconds from now, dive into the Circ UT. And we're going to set this up, and all we do is we set the burn UT here to say start burning at that time, and we say circle. Circ UT is a little more complicated. So it comes through and it uses mode 1. It says if mode isn't 1, set mode 1. Notice down here, when we call this again later, mode is going to be 1, so we're not going to do this code again. So we go to mode 1, first time through, it says, we know it's self.burnUt is set. So we call self.burndv for right now. If I were to circularize where I am standing right now, I am at, 71 kilometer altitude. I've got a apoapsis 80 kilometers. But what would my delta V be? What burn would I need to make right now to circularize? And we're going to stash that away. Now, the important thing is that that's going to be a guide for where we want to point the rocket. We're going to point the rocket along that delta V line even before the burn. So we're going to start with our nose kind of pointed roughly the right direction. The closer we get to our burn time, the closer our nose is going to be to where we want to burn. So when we get there, we'll already be lined up. Go to autopilot, and we say target orientation is, we don't need to set it twice. That can be corrected. That's a bug. So target orientation is along the burn DV. Now, if burn DV is 0, this is going to give us a bad day, but burn DV is never exactly 0. It may even be tiny, tiny, tiny. Yeah, if it is tiny, we're going to end up bailing out very soon. So we would only get a blip from our attitude control. Then we establish a throttle provider function. Now, bear in mind, we're doing this when we are just outside the atmosphere, and it's going to be a while. It's going to be a couple of minutes before we get there. But we're going to do this now. We're going to set up our provider. So each time through, it's going to do this calculation again. It's going to find out what DV we would need if we were going to circularize right now. Okay? It's going to save that inside the orbital structure. So we've got state for the other orbital functions. So we're going to save burn.dv. So we're going to keep that stored. And then we're going to update the autopilot. So even, no matter what else we do, the first thing we do is we are making sure that our nose is pointed right along that burn vector. We're going to say, well, if it's not time to go yet, leave the throttle at 0. So there's our early out. So until we get to the node, we're executing only this much of the throttle provider, which says keep us pointed and no throttle. Once we get to burn UT, then we can do the rest of this, which says figure out our maximum thrust. Our actual thrust is the delta V we want times a gain. There is a gain in the controller here. This is a proportional controller, and the gain is 1. In this case, the gain is the ratio between the delta V you want to achieve and the acceleration you want to use to get there. So I'm saying basically if we want a 10 meters per second delta V, I'm going to use 10 meters per second of acceleration. Okay? So there's an implicit gain. So if we wanted to tune the gain, I would have to add another multiply in here. Just add a KA or something. So we want to convert that to thrust. The way you convert acceleration to thrust is you multiply by the vessel mass and divide by the maximum thrust. So if you multiply by the vessel mass, that gives you the force to achieve the acceleration. And force divided by maximum thrust, which is a force, gives you a number in the range of 0 to 1 for how much thrust you want. And maybe it's bigger than 1. Now we limit that to the range 0 to 1. So now we have a throttle command in the range of 0 to 1, where 1 is give us full thrust, and maybe we need to do a whole lot more burn than that, but we're going to run full thrust. And as our DV gets small, that's going to ramp down. Now, applying to that, what if we're not facing the right direction? If we're bumped so we're like 7 or 8 degrees offline, if we're not pointed along the correct line, we want to reduce our thrust. And the further we're pointed away from it, the more we want to reduce it. In this case, I've elected to say full thrust. We can go full thrust as much as 1 degree off. More than 1 degree, we want to roll it down. And more than 5 degrees, I don't want any thrust more than 5 degrees offline. So this gives us a nice ramp from 1 degree error to 5 degree error, which decreases AFRAC from 1 down to 0. And our final computation is simply to take our throttle command 0 to 1 and discount it because we're facing the wrong direction. That's the value we put into thrust. So this gives you a nice, smooth reduction in your thrust as your remaining error gets small. Okay? And a bigger reduction in thrust if you're pointed the wrong direction. So that sets that up. This will ramp your throttle down to 0 when you're about done, even if we don't get called back. So this runs very, very fast relative to everything else. So that's all only the first time we call cirqt. And every time we call it, we're going to take a look at this burn DV that's been stored. Now, we started off by storing a DV value in there, and then every time the throttle provider runs, it'll update the DV value. So now we're going to look at this and we say, if the delta V error is bigger than 0.1, so if we need more than 0.1 meter per second fix, then call us again. 0.1 meters per second is a very small delta V, but even the biggest engines, we can throttle them way down and blip them real quick and get that kind of precision. And if we can't, I will work on this, maybe making the delta V, somehow compute the minimum delta V that can be achieved with the current engines, the current thrust, the current mass, and so on. It would be more calculation. For now, 0.1 as a threshold gets me very, very close. Now, if we're under that, then shut the throttle off, tell the steering to keep us steered prograde, and false. So when we're done circularization, we're going to point ourselves prograde. Now, if we were descending into an orbit, our burns would be retrograde. So what we're doing is Before the burn, we'll slew around to retrograde and we'll get ourselves pointed and we'll do the burn. And when it's all done, we'll snap back to prograde after we've settled into the new lower orbit. And that should work just fine. If we wanted to stay retrograde, maybe we do something here to say, well, decide just before we do this as to whether we are closer to prograde or retrograde and set the SAS appropriately. Anyway, so that's it for the circularization. The one I didn't cover was circdv. This is just pure math. We cover all of our constant stuff. We get our current radius and calculate the speed of a circular orbit at a radius, which is a constant. It's the body mu divided by the radius square root. We look at our current velocity. Now, our circular velocity is going to be the proper speed, but we'll have no vertical components. So the first thing we need to do is work out what direction our circular orbit needs to be in. So we take vessel.up. Vessel.up is the vector away from the body. So from the vessel, away from the body. So we're going to take that direction. And whatever component of our velocity is in that direction, we're going to exclude. So vessel up exclude from V old will snap our velocity to just that plane that's parallel to the surface. And we're going to normalize it so it'll be of length 1. So V hat times the speed we want is going to be the velocity we want as a vector. So dv is the velocity we want, horizontal at the proper speed, minus the velocity we had, which is our orbital velocity, which may be up or down. And that dv is our result. I prefer to calculate, toss it into a variable, and then return the variable. That way I can print out things. I can do things like go in with my editor and then stripe down through and say const x equals something, put out something out here that says print x. Real fast for me to do. And you get all the values. So stretching it out like this is a debugging aid. If it turns out that collapsing it has a performance win that is significant, I will think about doing it. It's going to take a lot for somebody to convince me that that's a performance win. I don't think it is. I don't think it ever will be. So keeping it like this keeps it clear, keeps it debuggable, keeps it so I can print things out. And that's it for circularization. Okay, so I think we have covered all of the code. Here's circap. When we're done, we use a phase function that just returns true. So it's just going to say call this lambda repeatedly. So it's actually this lambda that's getting called. It's unfortunate that I have to write it this way. What I'd like to do is instead of writing a lambda, I would like to pass a reference to the function, just like that. Now, this language is mostly functional, and yet the function name doesn't appear to be a first-class citizen. Let's see what happens when I compile that. Let's stop the guy that was running. Now, when I hit reboot, it says that launch doesn't have a field called manual. Well, it's got a method called manual. So if I say manual without the open brace, close brace in my head, that should get me a reference to the function, which looks a lot like a lambda. So this should be roughly the equivalent of this, but it's not. I may need to talk to the mod author to see if we can work out in the language how to convert directly from a method name to a reference to the method, even if there's some stuff involved there. But I want to get away with doing it without wrapping it inside a lambda. because among other things, I also want to retain type information like the function, whether it's sync or async. Currently, the lambdas here, fn, whatever, these are all sync. They have to be sync, which means I'm forcing my functions here to be sync. I'd like these functions still to be async. There's nothing about anything I'm doing here which requires them to be synchronous, except for the fact that they are being passed through a lambda. So I need a way of doing a pointer to a function that's async. And I'm retaining these two lines commented out because other scripts are going to want to go through there, and I want to just be able to uncomment them and have them work. So reboot, we're back to working again. I am going to let this run one last time with my edits to verify I didn't break anything. And I'm going to put this on mute and have some dinner. Clear. Reboot an extra time just for fun. And here we go. Waiting launch. Let's try that again without the code editor in the way. Okay, and there we have it. The final scripts with the final edits took us into orbit nice and smoothly and got us circularized without any fuss at all. And with this particular configuration, which is fairly modest, we still have 3,212 meters per second of delta V available. Now, once the asparagus staging is fixed, that number will go up. This 7-engine configuration for asparagus is actually quite a nice launch stage. It basically means I can use this configuration to do just anything I want to do, at least here inside Kerbin's SOI and maybe a little outside it. I'm not sure how far we can get interplanetary, but it does mean that once we do need to go farther, we can go and use similar asparagus configurations of larger tanks and larger engines and pick up a lot of delta V. But for that to work, the fuel lines have to work properly, and we have to get proper estimates from here. Because right now, to get correct estimates for what we would get in delta V if the ducting was working properly, I have to go to a spreadsheet. And because I can't characterize what the ducting is currently doing, I cannot estimate the actual delta V with the spreadsheet. But getting over 3,000 delta V available to us on orbit is more than enough for this craft to head out to Mun or Minmus, especially if we launch into Minmus's plane. We have, it's an easy jaunt out there once we've gotten into its orbital plane, as long as we don't get trapped by Mun. So the next few scripts I'm going to be working on, I'm trying to mirror what I've done in KSP-1. And at some point I will catch up, and then we'll be developing in both games in parallel. KSP-1, I am currently thinking about setting up satellite constellations and the best way to do that. And I think I'm going to wire that in with some changes to how I handle my offsets from my targeting. So you say destination is this vessel, and instead of this vessel plus 100 meters toward the body, it's going to be this vessel plus 60 degrees forward in its orbit. But anyway, so our goals from here on is to get the Tinker script so that I can basically select an orbit, periapsis, apoapsis, inclination is where I'm going to start. At some point, we'll add in specifying the argument of periapsis, and we'll specify the longitude of the ascending node, which gets the orbital shape perfectly. The longitude of the ascending node is going to control where the orbital plane is, and the argument of periapsis says where along in the circle the PE goes. So until we nail those two down, the periapsis could be anywhere. For instance, if I want to do a Molina orbit, that's an orbit that is highly inclined and goes very close in the southern hemisphere and then goes very far in the northern hemisphere. This is used by Russian communication satellites so that they loiter at high latitudes to give coverage to most of Russia, most of the USSR area, and they aren't that interested in communications in the southern hemisphere, so they just they focus on that. You can get good coverage of fewer satellites that way. I think that's what their reasoning is. Anyway, it's also a fun orbit, but what that means is to get that orbit properly, you need to control the argument of periapsis so that your periapsis is down here in the southern hemisphere rather than being in the northern hemisphere. You get the right orbital plane, but if your periapsis is in the wrong place, oops. There's ways of doing that. I've worked out the math in KSP-1. We'll just move the math forward. Now, the fact that we don't have a setter giving us contracts means I'm going to need to work out these myself. And maybe what I'll do is I'll just play parallel campaigns in KSP-1 and KSP-2. And when I get a contract in KSP-1, I will work to mirror that in KSP-2. It's going to make it hard for the rescue, because for a rescue, now at KSP-1, we've got a vessel to rescue. At KSP-2, I'm going to have to launch the guy to be rescued and get them into the appropriate orbit and then launch the rescue mission. So it could be kind of interesting. Launching the guy to be rescued, well, that's just a matter of launching a satellite, right? Except it happens to be a satellite that has a passenger on it. Anyway, that's enough for now. I'm going to shut the stream down and go putter around for a bit. I will see you all next time.